In this video, we're going to talk about what might be one of the more complicated parts of trying to model with differential equations, and that's trying to write the actual equation that fits a given physical problem. So beyond tank problems always have the same setup, other modeling problems aren't always as straightforward. So in these contexts, you'll be given a word problem and then asked to solve something, predict something, analyze some result based on first taking that word problem, find the equation that fits it, and then solving that equation to go forward. Solving the equation part, usually not too bad. The issue is setting up that equation in the first place. So what are you looking for when you read a problem trying to figure out what can I learn from this to write my equation model for it? So the first thing is you always want to take into account rates of increase and decrease. So what is causing this to increase and how does that affect the rate of increase? What's causing it to decrease? How does it affect the rate of decrease? For example, if something caused the quantity to decrease, the result of that term had better be negative when it shows up in your equation. Whether that means it's naturally negative or it comes in with a minus sign attached to it, it better be negative. It's going to fit the right model for this scenario. The second point is the use of the word proportional in this context. So if a rate is proportional to something, that means when it shows up in the equation, it will have some proportionality constant, usually the letter k, on it. And usually you have to solve for that k in the context of the problem to be able to carry out the work. You also want to keep in mind what is going to be involved here. What are the quantities? How can I talk about the rates of change? What can I use to write this equation? And as a last point again, I will mention the sign of each quantity. Again, increase versus decrease matters in how you set up your equation. So let's look at some brief examples of things you might want to set up and what that looks like in terms of the equation itself. So our first example here says that velocity is proportional to the position cubed. Velocity starts negative, position starts positive. As x goes to 0, up goes to a slope, where x is my position here. So our key thing here is x is position. And I'm giving information about velocity. Well, x is position, what's velocity? Well, velocity is just dx dt. And so for first example, we have dx dt is proportional to velocity cubed. So proportional to means some constant k. Position cubed means x cubed. Now what does that second bit tell us? Well, it tells us that velocity starts negative, position starts positive. Well, that's going to tell us right off the bat that k is going to have to be a negative value with the current setup that I have. Because then my dxt is going to be negative. And then this last bit then makes sense because as x goes to 0, the object slows to a stop. As x being positive goes to 0, velocity should still be negative and get smaller and smaller, which it will, because when x goes to 0, the velocity here also goes to 0. So we either have a setup like this, where I know k is going to be negative constant, or I could rewrite this to use dx dt as just negative kx cubed, where now k is going to be a positive constant. Normally, you'll want your k's here to be positive constants. It makes it easier to solve things out, but either way works as long as you have the signs right in the problem that you have. For number 2, we're told that population increase is proportional to current population times m minus population. This is a carrying capacity logistic model. So our setup here is that p of t, or p prime of t, or dp dt, is proportional to some constant k, population times m minus population. So there's your logistic model. It makes sense that if p is positive and not bigger than m, population will grow, so the k here being positive fits with that description. For 3, vertical velocity, proportional to the square root of height, and height is going to be decreasing over time, with h being the height. So for that, we know that my vertical velocity is the change in height as a function of time. It's dh dt. My vertical velocity, dh dt, is proportional to the square root of the height, h. And I know that height should be decreased, which is my dht should be negative because it's falling down. So I want to put a minus sign here in front to match the sign convention here that I want k to be a positive constant in this scenario. There's three ways how you can break down a sort of reduced word problem into an approach that'll let you write the differential equation for it, and then you can hopefully from there solve these out. Right? For all of these are all separable. They're all solvable at this point. So you can know how to solve separable equations. You could solve these and figure out then what's happened over time to the different models based on the setup here and the solution you would generate for this differential equation.